Welcome to day 5 of the vectors unit. We're on to vector subtraction number 2 today. I'll just give you a second to look at that and get yourselves ready. All right, so we talked about vector subtraction last day a little bit and looked at a few problems. So we're just going to do a couple more examples today to hopefully try to get you to understand this a little bit better, because it is a tricky topic. So this first example basically provides you a diagram of 3 vectors. So looking at this first example, we have vector A bar, vector B bar, and vector C bar. Okay, notice there's also arrowheads pointing in a specific direction here. So if it's hard for you to see, vector A is pointing that way, vector B is pointing that way, and vector C is pointing that way. So the idea is to express one vector as a difference or a subtraction of the other two. So it's kind of a weird thing to wrap your head around to begin with. So if you just kind of simplify the question, think about if I gave you 3 integers, 1, 2, and 3, okay, and I asked the same question, express one integer as a difference of the other two, that wouldn't be too difficult, right? We could do 3 subtract 1 equals 2, right? So that's a way of taking 2 of these integers, doing a subtraction, and ending up with the other one. Okay, and it's asking the same question. Can I do A bar minus B bar to get C bar, or A bar minus C bar to get B bar, or what combination? What's the proper way of arranging them such that the subtraction makes sense? And we kind of have to think about what we did last time, and that's that when we subtract, it's the same as adding the opposite vector of the other, and we just flip the vector around. Okay, so let's just for trial and error, and we can maybe try a different approach next time, let's just think about what if we were to do A bar minus B bar, and does that actually give us C bar? Okay, so let's think about that. Okay, so we have A bar pointing that way, and we're going to subtract B bar. Okay, that's the same as adding the opposite vector of B bar to A, and hopefully that gives us C. Well, what is the opposite of B? Well, the opposite of B is just basically flipping the arrowhead and the tail. Okay, so if I erase here, and I take this vector, and I just flip it, so now it points the other way. So now this is negative B bar. So if I'm adding A bar and negative B bar, our resultant should be going from the base of A and finishing right there, which is, yeah, exactly what C bar does. So A bar minus B bar, or adding the opposite of B right here, gives us C bar as the resultant, right? This is the result of doing A minus B. Okay, so this statement is true. Okay, that's a true statement. Okay, if we were to look at another arrangement, if we did C minus A equals B, I don't think that it would work out. You can kind of do that as an exercise just to see if the vector diagram works. Okay, so looking at B example, W, U, and V, can we think of doing this a certain way? So basically what we're looking at here is looking at which of these vectors should I be flipping or reversing the tail and the head of, such that when I do tip to tail of 2 of them, the third vector looks like the resultant. Okay. Sort of a weird conceptual thing, and there might be a couple different ways that you could do this. Okay, so immediately I see here that if I do V, which is pointing this way, W is originally pointing this way, but if I flipped it, it would then be tip to tail, and U looks like it starts at the base of V and ends where the tip of the opposite of W would be. So that one would work. So let's just kind of double check that by drawing it out here. Okay, so we have V bar. Let's try flipping W bar. Okay, so let's actually flip the arrow ahead of this guy. Okay, so now we have, this is negative W, and it's pointing that way. So you can see now that V bar and negative W bar are tip to tail, which is how we need them for adding. And the resultant is going to start at the base of the beginning vector, and it's going to end right there. So this is the resultant. So that makes sense. So if we do V minus W, that gives us U. And I think there's a few examples like this in your textbook if you're still kind of struggling with this idea, but it's basically just conceptual. Can you visualize this vector subtraction through three vectors just given as arrows? That's the idea. If you want to pause it now to kind of catch up if you're still writing. If not, we're going to move on to the next. All right, so this question, I guess, should be example 2. Change that. Looks like an example we did last class. Pretty much exactly, just with different values. And it was a tricky one, right? We had to go through a bunch of calculations to get to our answer, but ultimately we're given the information for one vector. Well, actually, we're trying to, so what are we given? We're given F2 has this magnitude, and it has this bearing. And we're also given that the resultant has this magnitude, and it has this bearing. Okay? And the goal, the end result, is to figure out some information about F1, namely its bearing and its magnitude. Okay? That's the end result. So we're given the magnitude and direction of 2 vectors. One is F2 and one is actually the resultant. So we kind of have to go in reverse. And if you remember from last day, we made this a vector subtraction just to make our life a little bit easier. So let's start off by just drawing this as a diagram here. So starting with F2, I guess. We're given F2 is at a bearing of 220. So if we start from north, if we go clockwise, east would be 90 degrees, south would be 180. So we're going to be about 40 degrees past that. So approximately that direction. This is our F2 vector. So this is F2 right here. Okay, we're also given that F1 plus F2, the resultant, is at north 50 west. So starting at north, going 50 degrees towards the west, and this one should be a little bit smaller in magnitude than F2. So the arrow should be a little bit shorter. So approximately that way, we're a little bit shorter, and this is F1 plus F2. Just like that. All right, so at first glance, we can see that this looks like it could be a 90-degree angle, but again, that could just be the way that we've actually drawn this diagram. So we could, if this is something you notice right away, if we can actually figure out if this is exactly 90, this might make our question a little bit easier. Okay, so in the next video, we're going to kind of continue this question on and finish the question.